Well, to have some kind of like a recap or something to remember, I've got here like a summary of the distance functions for you. So we have the distance or similarity computations, and then we have the computations in ambient space or data space is another name, and computations in other spaces. So computations that are in the original data space are like either Mahalanobis style, like for C-CoPark SSC as an example that we've seen, or they are like in Oculus or LM class. However, those like they are also overlapping here. We say SSCC, Oculus and LM class, they compute distances between an object and a subspace or prototype within a subspace. So here, for instance, LM class computes the distance of an object to a subspace, to this also a normal basis. Oculus computes the distance and SSCC also the distance of an object to its prototype, to its mean, either in correlation or in cluster subspace, in the orthogonal one. And here for C and CoPark, they compute distance between two objects, P and Q. Then we have here like in eigenspace for the independent component analysis, ICA, we have sonar, and in half space, the computations we have like cache. So this is what we have here as a summary, so to speak. And now we move on to the parameters. So far we had the distance functions, and now we say what are the parameters, because the parameters enable us to control the properties of the outcome of a clustering. So how they actually look like, which properties they fulfill. And we ask you which properties of the resulting clustering can be actually controlled. And for this, we have this formalization that we are given a set of objects from a data set, D. Further, we are given a correlation clustering algorithm, gamma, and a set of cluster affecting parameters, kappa, and a set of subspace affecting parameters, sigma. So the task of correlation clustering, now this is a hyperparameter focused view on the correlation clustering task. It is to obtain a partitioning, a clustering with its respective subspaces. So we say an algorithm gamma on a data set D with parameters that affect the clusters kappa and the subspaces sigma yields us a partitioning C with the single clusters C0 to CK and their corresponding subspaces S0 to SK, such that for all of these clusters, it holds that they satisfy the cluster affecting parameters kappa, and they satisfy, so for all subspaces, it holds that they satisfy the subspace affecting parameters sigma. So this highly parameter or hyperparameter centric view of correlation clustering says the goal of correlation clustering is to find a partitioning which finds a result that satisfies the constraints that are given through parameters that control or affect the clustering, like the partitioning itself, and that satisfies the parameters that affect the subspaces. And here you may rightfully ask, what is now a cluster affecting parameter and what is a subspace affecting parameter? We shall see it within the upcoming slides. So here we have like, again, our known algorithms, and you see like, for instance, min size, the minimum size of a cluster. This is something that affects the cluster, or the number of clusters, K, this affects the clusters, or the minimum points, again, like how many functions should go through it, through that section in half space, or the epsilon range and min point, or like this K and gamma, which is like for number of clusters and like the support. So all of these properties are things, or like here also K, mu, and epsilon. So the different parameters, all of them are affecting like the numbers or how many objects are within the cluster. They affect the cluster themselves. On the other hand, we have like subspace affecting parameters like L in Oculus, stating what is the dimensionality of the subspace. Or like here S and J is stating how much variance do we tolerate in the subspace, how much variance in the one direction, how much variance in the other direction. Or here in 4C, kappa and delta for the deviation and lambda for the maximum dimensionality. So these subspace affecting parameters mostly control like the variance or the deviation, the jitter, so to speak, and the dimensionalities that we have. Here also LM cluster dimensionality. So these are the two categories that we introduce here. Say we have cluster affecting and subspace affecting parameters. And how are they related? Because we have now these different parameters, but can they viewed, are they only to be viewed isolated, like there is a min size, there is an KNN or something, or are they by any means related to each other? And here, let's go through some of these examples, like support of clusters. We have here minimum, mu, and min size. And we have here like density of a cluster. This is like epsilon and the KNN. So the hyperparameters which mediate the support, so the mu or min size of a cluster. So these are like different parameters. So you have like in one algorithm, if you go back here, you've got like mu, and here you have like min size in SSCC. These parameters are characterizing the support of a cluster. They also mediate the density of the cluster, which is characterized by parameters which control the epsilon range or the KNN neighborhood. So you have like here, epsilon or KNN, these are parameters which tell you like how dense is it, how small or how large do I wish to have the neighborhood. And up there they say how many objects do I wish to reside within a specific area. And here you see, depending on how you choose it, you would either get like this one, like these small cluster patches, or if you would increase the min point, then you would detect like this one big cluster. So it highly depends of how you mediate support and the range for the cluster. Actually, both of them. So if you say objects per surface or per volume, you kind of mediate the density, because from a physical point of perspective, you say the density of an object is defined through number of atoms or particles within a certain surface or volume. Then we have hyperparameters which affect the support of cluster, like mu and min size, and the tolerated deviation from clusters. So we have a relation between these two sets of parameters. And tolerated deviation, we have like this delta, kappa, gamma, S or J from cache, for instance. So how are they related? Well, the support of clusters influences the tolerated deviation of objects from a cluster. And this influence is like of twofold nature. So one, the larger mu is chosen, so the support of the cluster is chosen, the potentially higher is the chance that the objects deviate from the subspace. And as such, the hyperparameters like S and J, so like this jitter that we take here, have to be chosen in such a way that they permit more deviation from subspace. So if I say, you know what, I wish to have like 2 objects or 3 objects, then a jitter of 0.1 is perfectly fine. I've got like 1, 2, 3 objects in here in this red band that you see here, it's all fine. But if I say, you know what, min size, or I want to choose as 4, then this one here is no longer satisfied and I'm kind of forced, so mu or min size 4, I need to choose a larger tolerated deviation, J equals 0.2, so a larger band. This is one relation between the support of clusters and the tolerated deviation. If I demand a higher support, it may happen that I need also to increase the tolerated deviation from a cluster or from a subspace actually, because it's not only from the cluster, but from this subspace SM. Then the second from this twofold part is increasing mu. So the support may lead to the phenomenon that among an increasing number of dimensions in an arbitrary oriented subspace, so the variance grows beyond a certain threshold like delta, and this makes you flip from a line to a plane, to a higher dimensional emerging subspace. Again, difficult to imagine. So suppose we've got here this subspace, we've got here mu equals 3. And we would say, okay, you know what? They are having a deviation that is small, so we can say they are located around a line. Then depending on the algorithm, you say, no, I want to have min point support 4. And then we have too much of a deviation that we say, like in 4C, for instance, you know what? It's no longer of dimensionality 1 because we have too much of a deviation, but instead we now say it's a 2-dimensional correlated cluster because it's now located on a plane. So the demanding of the support of a cluster may also influence the dimensionality of the cluster from dimensionality of 1, this line, to dimensionality of 2 here, plane, by increasing the minimum support. Then we have another relation, which is this time mutual, between tolerated deviation from cluster and dimensionality of clusters. So the more deviation is tolerated, the more variance per axis within the arbitrary oriented subspace, and therefore more dimensions are needed to satisfy a certain threshold alpha. And on the other hand, the higher the subspace dimensionality, so the higher I choose lambda, the lower is the needed tolerated deviation from a cluster. So to flip back to this one figure here, if I say, okay, you know what? So I dictate and say the dimensionality of 2 is fine, then I do not care about the tolerated deviation. So I say that may deviate as much as it want, I do not care, because I have a higher dimensional representation that these objects may reside in. On the other hand, if I say no, I want to have them as close as possible, then I enforce it to be of a certain dimensionality. So the higher the subspace dimensionality lambda, the lower the needed tolerated deviation, but also the more deviation tolerated, the more variance per axis, and therefore more dimensions are needed. And about this more dimensions that are needed to satisfy a certain threshold, this is something you will see in the upcoming slides of a different chapter. So I've got nice illustrations for that. And we have here now the relation between the number of clusters and the support of clusters. So the number of clusters, this influences the support of clusters. How that? Well, we say the maximum number of clusters K is the entire size that our data set has divided by the min points. And on the other hand, the min points on average, that on average like each cluster can have, is like the entire database divided by its number of clusters K. So if I say I wish to have like a lot of min points per cluster, then of course I will have fewer clusters K. On the other hand, if I say I want to have like a lot of clusters K, I will have fewer average min points per cluster. So an upper bound for the number of clusters K, given a minimum threshold for a number of objects supporting each cluster, is the database size. So we say we cannot have more clusters than we actually have number of objects in a database, divided by the min points mu, and the average number of objects assigned to a cluster is the database size divided by K. So these are the relations that we have here between support of clusters and number of clusters. I mean, probably for you, you may say, oh, come on, this is trivial. Nevertheless, it's important to know that if you say you want to have a lot of objects, high min points, then the number of clusters gets smaller. And on the other hand, if you say I want to have a lot of clusters, then min points will shrink on average, or on the other hand, it will increase. If you say you wish to have like fewer clusters, then you can have a higher min points on average. And I think the last aspect that we have here about mutual influences on hyperparameters, here we have a relation between tolerated deviation from clusters and the quality of clusters. So the mutual influence between tolerated deviation from clusters and the quality of clusters can be regarded as the following. The example of the sampling size as from LM class, it says that a large number of samples taken from the data would minimize the effect of outliers, because the more objects you take, the lower the probability that an outlier skews your orientation of your subspace. And from the perspective of the tolerated deviation that we have here, it means that the more deviation is permitted, the lower can be the potential quality and the lower can be the chosen sampling size S. So if you say you want to have high quality, you want to have a lot of computation steps, or you want to have a lot of samples S, then this will mean that you have lower tolerated deviation because you're sampling more, for instance, in this particular case. But on the other hand, if you say, yeah, I actually allow more deviation, it's okay that the objects are not perfectly around a line. I do not care if the subspace is kind of like a bit rotated more or less or translated, then it will have an impact here on the quality, and you can say, I do not need that many samples. And it was not the last one, but this should be, I hope, So we have like the support of clusters and the quality of clusters. The cluster quality influences the support. So if we choose a large sampling S, as we had before, then the minimum number of objects supporting that cluster increases as well. So if we say we want to sample 500 objects, then in that particular cluster, there also should be at least 500 objects. And taking all of these single puzzle pieces together, we get this figure of what is related to which parameter. Also here, you may now think, I really have to learn all this stuff. No, because one cannot actually keep in mind all of these single parameters and what you should take here as a take-home message. They can be relations. They can be relations regarding support of clusters, density of clusters, quality, number of clusters, dimensionality, and tolerated deviation. So these 6 aspects you should have in mind, not all the single letters. And what you should also have in mind is like the distinction between cluster affecting and subspace affecting parameters. So through this parameter-centric definition of subspace clustering here, that you find a partitioning such that these cluster and subspace affecting parameters are satisfied. These 2 categories, like cluster and subspace affecting, and here these different categories, tolerated deviation, dimensionality, and so on. These things are to keep in mind. The single letters and which algorithm has which parameter, again, I do not care. This is something that you will look up if you really need it. But having this higher order, this like more abstract or high level things of support of clusters, density of clusters, that is what matters to me. Well, and this is it. And see you in the next short clip about different views. Thank you.